Okay, we proceed to the next paragraph, paragraph 2.3, about geostrophic flow. And before that, it is interesting to show, okay, it's interesting to show from the previous slide. As we noted before that in the equation 6 and 7 and in 5, that since the Rossby number, which is 2, 6, this Rossby number, and Ekman number, this is 1, are very small in 5. In 5, it's actually the system which we are solving. So this epsilon number, in fact, Rossby number is about 10 to minus 6 in the Earth, I remind you. This Ekman number, if we take into account molecular value, it's 10 to minus 15. And on my previous lecture, I also told you that while this Ekman number is much less than Rossby number, but nevertheless, we cannot omit that, because actually this value is linked to the boundary condition and with the highest order derivative. So it's small parameter near higher order derivatives. We never it will be neglected maybe in the second instance, but in the first instance we should neglect back the Rossby number. But why not to examine the flow where we neglect by both number? Why not? With this system, of course, we obtain some reduced system, but nevertheless, it's possible to solve it. In some sense, it's the mostly idealized system, and we can get it from this system 2.4. is with the condition that Rossby number is small, Ekman number is small. So why not to neglect by both of them? So now we proceed to the subject of this lecture. Okay, so after this, I just repeat that since Rossby, and again, in accordance to the formula 6 from the previous chapter, is small, and Ekman number is also very small, and it's a very small number indeed. So are very small in the initial equation 5, which I just showed to you. So the transition from the differential equation from 5 to relatively simple, so-called geostrophic equation, formally obtain it, so it's in some sort of sense of formally we obtain it, we just equate to 0, Ekma, epsilon, and E, so consequently Rossby number, and all the terms which connected with it. Of course, this is quite big term which cause a lot of troubles, and it's just simply 0. And also we neglect by viscosity, so we obtain some idealized system. And eventually we have this set of the equations. Let's write it down. So of course we start from the 0, because actually this 0 actually is obtained here after when we neglected by the substantial derivatives. And front of substantial derivatives is this epsilon, which is Rossby number. So we are free to put 0 instead of the substantial derivatives. Then the term which is definitely remain, this is the Coriolis term. It's remain because actually this is the most valuable term in this approximation. Then it multiplied it by the cross product on the z, unit vector of z in the axis of rotation, which is directed in the axis of rotation. And of course we should put minus pressure, more precisely somehow reduce it or normalize it pressure, normalize it with density, so there is no density anymore here. But nevertheless, while it's normalized pressure, further I will call it simply pressure, just to avoid some extra wording. So, and of course the divergence is also equal to 0. Divergence of V is equal to 0. And this is formula 2.8. So this is exactly the formula for the geostrophic flow. And actually, you see that in this condition we have actually we are working perhaps I'll better do it with the mouse. Yeah. Actually, on this condition, we are working, in fact, we are working not in spherical coordinate system, but in cylindrical coordinate system, because we have the specially stressed situations that we have some direction which is preferable. And this is direction in the direction of the axis of rotation, this z component is directly in the axis of rotation. So, and everything rotates around it. So we have more, of course we can use spherical coordinate as well, but in the sense of the physical nature, it's more easy and more profitable in this geometry to use cylindrical coordinate. And here on this picture you see that the cylindrical radius is denoted by small s, and and other coordinates are the same as used before. And nevertheless, we can proceed to the general solution of this system. It's a big advantage that it is simplified system which I just show you, has a general solution. And so the general solution of the system of equation 8, this equation, is most conveniently written in a cylindrical coordinate system. So actually this cylindrical coordinate system is coordinate system in which we have the variable, of course, starting from the z. Then the next is cylindrical radius, s small, and also there is a phi azimuthal component, and it's important to know that this phi is exactly the same phi like in the spherical coordinate. So it's exactly the same phi. So this is somehow united spherical and cylindrical coordinates, that there is one variable which are common for both of them. So, and actually you see here in this picture how it's work. So, and of course we can relate to the spherical coordinate all this stuff by very simple formula. So this z, we can write like that, is r cosine theta, and this s is consequently r sine theta. And again, I stress that the azimuthal coordinate phi is the same in both systems. Is the same. I just put the explanational mark here. Let us write out for details see the solution of problem of the second problem devoted to this particular chapter. And but at the moment we just directly write all three components of the first vector equation from system 8 in cylindrical coordinate system. Here we have in the vectors system, but more convenient to write down this equation in the cylindrical coordinate system because it's quite natural for this geometry, and it's shown on figure 4. So we just write down this system. And of course we start with 0. And first of all we consider the component which is in direction of z, of the axis of rotation, the z direction. And of course this component of this equation 0 remains 0. And then we have this component which is actually perpendicular to this z. And you know that the cross product of cross vector product of the vectors which are perpendicular to each other is also equals 0. So the only thing which remains here is very simple, and this only thing is minus dp by dz. Let's proceed to another spherical, another cylindrical coordinate. And the next cylindrical coordinate, here this especially, it's important to note that here especially the order of how these coordinates are appears is very important. And here we have right-hand order, right-hand screw drive order or something like that. If you take the screw and rotate from Z to the S, if you rotate like that, you see that this screw, you will go in this direction if you have right-hand screw. So this is direction exactly. So we rotate from this to this, and then we get the direction in which this azimuthal coordinate is changed. So we use this rule of right-hand side screw. It's also important to understand how all these things work. And let's now write down the next coordinate. The next coordinate, it's necessary to see, of course, on the cylindrical radius. And I write down just the results. but for you, it is a problem which you show it in more detail how you reach that. But here I just write down the result, and the special task for you will be to understand how it's working in detail. But here I'm just write down the result, and this 1, 2, a half. It's this half coming from this 2 when we divided everything by 1 and 2, and it's dp by ds. And of course, in a similar fashion, we can operate with the azimuthal coordinate, and also in the same sense, as I told you, of course, this sign which we appear here and here, and here this, of course, very simple. Here the sign appear, especially with taking into consideration this right-hand side screw, and you should be able to show it in the every detail how it works. And it's interesting that if we consider now phi component, you see that there is again sort of the cross. When we consider S component in the component of the in direction of the cylindrical radius, we getting from the Coriolis contribution to the velocity the phi component, azimuthal component, and vice versa if we consider contribution which is coming from cylindrical component, then we have with sign minus, because it's also important, it's working from this screw drive rule. And here we have actual Lamé coefficient, which is going down here. You should be show this in the detail. And here we have dp by dphi. So there is again some cross. On the s coordinate we have a phi, and on the s while on the phi coordinate we have a c as a contribution of the Coriolis force. So this is constitutes the detailed formula which is possible to solve. It's formula 2.9. In every detail for coordinate. Now it is obvious that the azimuthal V phi, azimuthal this one V phi, and radial Vs. Radial I again stress not in spherical radius but in cylindrical radius. Component of the velocity do not depend on the coordinate z. You see that these both components are not dependent on coordinate z. This z coordinate which started the most important coordinate which constitute actually the cylindrical system, and are uniquely expressed through the pressure P. So this quite uniquely expressed through the pressure P. To find the vertical component with z, you see that here we have all the velocity vector actually have 3 components. At the moment, exploring the reduced Navier-Stokes equation, we involved only 2 components. Of course, there is a third component. How we can get it, this third component? Or maybe first if we consider in terms of the cylindrical coordinate. So this component which is directed along the axis of rotation is, what do you think, what we should use to get it? We already used Navier-Stokes equation. Which equation remains? You see? So we should use the divergence equation to obtain this z coordinate of the velocity. So and so we can just expand again in cylindrical coordinate system this divergence vector. So this divergence of the velocity is actually by definition in the cylindrical coordinate system is depend. It has very simple depending dv by dz. Here, because the coefficient, Lamé coefficient for the first coordinate is 1, so we have this value. Then Lamé coefficient for the cylindrical coordinate derivatives is s, so it's coming this way. And as well, it should come to the derivatives s. Consequently, we are, in this sense, we can put the divergence against the cross vector products. If on the cross vector products and the stress correspondent, we have sort of the cross, we take in one value and derivatives from another value, then we will take another value and derivatives from this initially one value, so sort of the cross. Not symmetry, but the cross, sort of the cross. But for the divergence, it's symmetrical function. If we consider the z component, so we are using namely z component of the velocity and z component of the derivative. And the same is working for the cylindrical radius. If we use s component, cylindrical radius component of the velocity, then we use derivatives, partial derivatives in cylindrical components. So in some sense, divergence is sort of the symmetric stuff, not like these cross products. So, and of course, we should also add the second component. The last component. The last but not least, of course. Okay, so it's equal 0. So eventually it's constitute equation 2.10. It's interesting to mention that using the coefficient Lamé is somewhat tricky, because actually we use this coefficient Lamé here like that, and here we have similar stuff. But when we using the same coefficient of Lamé in the phi direction, then it's just terminate one each other. So only one remains in accordance with the dimension. But here we cannot terminate because it's entered with the same cylindrical value. Here it's going with the same coefficient Lamé, but it's the extra coefficient which appear here just cancelled. So in some sense, this is working like that eventually. So substituting the velocity component expressed through the pressure from 9 into 10, so we have the velocity component, two velocity component, we can express if via the pressure and then put in this equation. So we have Vs, which is represented directly from the pressure, and then we have V phi, which also represented directly from the pressure. So if we put all this stuff there, we put. You can train by yourself, but I am again will write down only the final result. It will be your task to make sure that if we indeed install this and this into this, we are obtaining tremendously simple solution, which is going from this and this, and with some reduced form. So we are obtaining very simple solution, and very important, perhaps the most important stuff, in the geophysical flow approximation that divergence of the z component of velocity, this one, actually we use this one. And also we use these two. Substituting them to this place. And eventually we get simply 0. Very impressive result from my point of view. And but I didn't show the intermediate step. It will be your duty to do that in some task. So it's very simple formula. So in other words, if we notate it mathematically, it's written down like that. But maybe more important in physical sense, because this means that there is no any dependence, of course, in this approximation, of the maybe zero order approximation, or maybe first order, because actually we zero cancel it was. So it means that there is no dependence on the z-axis, at least for the velocity in this direction. Velocity in this direction have no dependence. So it's will take some fixed value in this direction, of course, if we consider it's in this direction. It's an important formula, and it's dissolve its own number. 211. Accordingly, the general solution of geostrophic equation 8. So after this step, we can write down the general solution. It's also big advantage. Equation 8 can be written in the terms of two arbitrary, or in other words, free two-dimensional function p and vz as follows. So we actually, from all this stuff, which we write down here, okay, I just show it like that. From all that stuff, we are getting the general solution. Again, I just will write it down, and it will be your duty to show in every detail how it's works. So it will be sort of the examination. So I just will write down. So we have on the first place, of course, we can have Vz, which is equal Vz, and it's necessary to stress that it's independent of z coordinate, so it's dependent only on s and phi coordinate. So this is sort of the arbitrary function. Two-dimensional. It's necessary to stress that it's two-dimensional, because initial problem is three-dimensional, but this arbitrary function is two-dimensional. Then there is another one comes in the play, and another comes in the play. So if we consider here, we consider the z component of the velocity. Let's next consider the phi component. And the phi component from this equation is equal to the derivatives in the cylindrical radius of the pressure. And finally, if we consider the s component, then we have now again, in accordance with this screw-drag rule, we have that Vs component is equal minus 1/2. Here it's always 1/2 pair dp by dphi. here you see again sort of the cross. We're getting one component, and the sort of on the cross we have the another component, and the same is here. We're taking one component, and on the cross have another component. And it's important to stress that the second arbitrary function appear, because actually from this equation it follows that pressure is also independent on the z coordinate. It's again, it's obvious result. Also, of course, needs some proving, and it will be your duty to prove that, to understand and to show us how it works. So, but here I just will write down the result. And this result is that the P is dependent only on cylindrical radius and phi. So this is, of course, also a rather important formulation, which formulates the general solution and dissolve its own number to 12. This solution. So, okay, let me stress again. What means the general solution? The general solution, 3D solution, of course, this is 3D solution. Actually, this general solution, it means that it depends on some arbitrary function. Because the problem is 3D, so arbitrary function should be 2D. It's the rule of all the general solutions. So that arbitrary contribution to this general solution in order to satisfy boundary condition, in order to satisfy other conditions which you impose on the system, on this system. Usually this condition is one time slower than initial condition. So let me stress that there is arbitrary function which we can choose. At the moment when we consider a general solution, we just put them as arbitrary. But further we will proceed, of course, to some particular case of this general solution, maybe most important case. Then we have, okay, let me stress it from the above to make some difference. So this is one, and this is the second. And depending on only these two arbitrary functions, we can get exact solution for all others. It's just necessary also to stress that there is no dependence on time. So from one point of view, it's even some advantage of this system, because we can vary in time all this value, for example, even initial function, and this other function which is expressed in this term will be momentarily follow the rule which on which we can develop this arbitrary function. So as for the simplified, so this general solution 12 is essentially the Prior-Taylor theorem. There is even the special Prior-Taylor theorem. And this theorem proves that the flow does not depend on coordinate z directed along the axis of rotation when the nonlinear and viscous forces are negligible. There is a theorem actually. And of course, I show you all intermediate steps how to prove this theorem. But some detailed steps I omitted. So it will be your duty to understand how this very detailed steps are working. And eventually you should prove the Proudman-Taylor theorem, because perhaps this is Proudman-Taylor theorem is maybe one of the most important, if not the most important theorem in geophysics, because actually it works not only in the Earth's core, it works in atmosphere, it works in in the ocean. So it's quite general formula, and the geostrophic flow, which is fast rotating, and when the this Rossby term, v grad u, and derivatives of the time could be neglected. So let me formulate it one more, that just for your understanding. This theorem proves that the flow does not depend on the coordinate z directed along the axis of rotation when the nonlinear inertial and viscous forces, it's necessary to stress that inertial forces are nonlinear, so it's actually linear solution, of course. And viscous force also we remove because it's actually has a very small Ekman number. In some idealized situation, we can do that. And so in our notation, if this theorem is working for the case when Rossby number or epsilon in our case is not, and when the Ekman number, which we denote like E, capital E, is also is not. So actually, why there is not? Because they just compared with the Coriolis force, this one, Coriolis force. And this Coriolis force I showed you in the previous slide contains FOD1 multiplier, and pressure also the same, and divergence also the same, but all other terms are contain only small contributions, so we can neglect them. Against I just should state that this Coriolis term is the most important, and first of all, it's balanced by the pressure. Okay, and it's linear. So for the simplified system 8, which I showed you before, okay, and here it's also shown. For the simplified system 8 and the corresponding general solution 12, this general solution. So simplified boundary condition must be set. You see that the problem is actually very severe problem. If you remember, for the Navier-Stokes for the Navier-Stokes system of the equation involving divergence, of course, zero divergence. For this case, we have to set 6 boundary conditions. Roughly, the amount of the boundary condition could be calculated if we take the highest order derivatives. For example, in Navier-Stokes equation, if we have this, then we have the highest order derivative. And this highest order derivative is 2. And there are 3 equations with this higher order derivatives. So we just simply multiply 3 by 2, and we get the number of the necessary boundary condition. But here situation is changed. We neglected by viscosity, so we omit 1 extra order of magnitude, which allow us to involve the extra boundary condition. Here the situation is reversed. We have the highest order in differential term, 1, just 1. And so and again, we have 3. So we actually have just, we should reduce the number of the boundary condition to satisfy this reducing system. Of course, in some sense, it's sort of the downgrade the importance of the solution. But nevertheless, in some general cases, especially when this Ekman number and Rossby number are indeed small, it's work and it's produce some maybe even too simple solution, but nevertheless very important geophysical solution. So the simplified system 8 and the corresponding general solution 12 simplified boundary condition must be set. The number of these boundary conditions must be several times less than the 6 boundary condition represented in 5, due to the fact that the order of system 8 with E equal naught is several times less than for the system of equation from 5. In 5 it is the full equation which I show you many times. I hope you remember it. I will not show you again. Physically, the most justified boundary condition for 8 are those that correspond to the obvious fact that the liquid does not penetrate beyond the rigid boundaries. Situation is actually even more severe. Frankly speaking, we don't able to say how exactly many boundary conditions we should impose here. So sometimes we can, in accordance with the real situation. But there seems no doubt that if we consider, okay. Nevertheless, there is almost no doubt that if we consider the velocity flow, it cannot penetrate from the outer boundary. So if we have the outer boundary, so it cannot penetrate from the outer boundary. It's always stop. And so is this corresponding mathematical relation which states that if we consider r component of the velocity, which is directed in spherical radius, it's important to know that the real boundaries are spherical here. So now the play is that we have considered cylindrical system, but the boundary condition is in spherical system. And the first boundary condition, which is the most important, is at the outer core, as far as maybe you remember, that we normalize the size with the radius of the inner core. So the outer core will have the dimensionless radius, which was specified by C. We did that before. And it's, of course, greater than 1. For the Earth situation, this is about 3. So it's about 3 times. And this, if this liquid cannot penetrate from the outer boundary, of course it cannot. It's a very simple formulation. We just put 0 here. And of course it cannot penetrate to the inner core, to the inner boundary. So we are sure that for the inner boundary, we are odd. When r is equal 1, it's also not. And this constitutes important formula 2.13. Accordingly, it's if we apply this two boundary condition, very simple two boundary condition, then we accordingly the geostrophic flow under consideration in the main volume is determined by 12. With boundary condition 13. This flow consists exclusively of differential rotation, not yet defined here. So actually, after this manipulation, it again will be your task. I will just show you the final result, but you should make this manipulation, applying this boundary condition, and to understand how this general solution works with this application. So it will be your home task, if you like, and on the okay, you have very many home tasks. You should proceed from every detail of this calculation in precise way. I omitted some of them, just jump to the result, but your duty will be to show in the every detail how it works. So it will be, so actually we can ask you to show for all of this stuff, or maybe just for particular part of this stuff. So it will be sort of the many problem which can be breaking on the small problem and general problem. So, and you should train yourself just to understand how it works. Hopefully you will did. You will do. Yeah, sorry, you will do. So accordingly, that trophic flow under consideration in the main volume is determined by 12 with boundary conditions certain. This flow consists exclusively of differential rotation not yet defined here. So finally, the application of this boundary condition, these two boundary conditions, is that Vz is simply not. It's a very interesting result. Then V phi is simply some function of cylindrical radius only. It's important to stress. Some function of cylindrical radius only. And now it's again arbitrary function. Then it's interesting to know that this arbitrary function related with the pressure. 1/2 dp by ds and I should stress that here it's not partial derivative, it's direct derivative, because p is dependent only on s, and this is consequences of the boundary condition. And also there is another simplification that cylindrical coordinate of the velocity is simply not. And as I already told here, that the pressure is just function of cylindrical radius alone. So actually we use two boundary conditions and reduce it to the very simple solution, which have only one arbitrary function. Only one arbitrary function. So if we impose the third boundary condition, or another condition, whatever you like, you can impose not boundary condition, but the condition which, for example, for thermal wind, there is different. Thermal wind is very popular in the atmosphere. Of course, in this case, you should add the thermal term as well. But nevertheless, it seems that the here game that we initially has a 6 boundary condition. And so if we reduce it almost 2 times, we reduce it the order of the system. So effectively, we should have 3 boundary conditions. 2 of them I already show you, and 1 remains. So this game plane is in such a sense that if we have arbitrary function, so you have actually could apply 1 more boundary condition just to identify this applicable this function. And sometimes it's not necessary boundary condition, because very often case that near the boundary some viscous layer appear. So you should match not to the very boundary, but you should match to the viscous layer, which is in this case usually Ekman layer, which we will discuss before. And you just apply this condition not exactly to the, you apply this boundary condition, sorry. Okay, anyhow, this boundary condition will work for that to identify this arbitrary function. Of course, there is another way. You can use not necessary boundary condition, but actually you can use some additional condition just to specify the pressure, and we show that. And very important, I get the, what I wanted to say. The important thing is that for this extra boundary condition, we should apply not directly to the boundary, but the upper. For example, we have some boundary layer, which lower part, let's just, for definition, suppose that the lower part of this boundary layer is directly on the boundary, but there is some upper part where the viscous boundary layer is actually disappeared. And we match this geostrophic solution not to the real boundary, but the upper boundary of this viscous layer. This is sort of the trick. And it's also needs some art to understand how it's works. So, okay. Yes, so in some sense, this general part of the solution can be specified as I already told, with consideration of, in fact, these terms which we omitted. So to understand how it, in some general sense, we are going to this step, and we stop here at the moment, and then now we should, there is no way to work in this approximation when Ekman number and Rossby number are not. To proceed further, even with such a simple solution, we should involve more higher derivatives, which will constitute some viscous layer, which is on the boundary, and which is which is on the boundary, and which show how it is working. But not only on the boundary. There are some shear layer appear, and the most important one is on the tangent cylinder. And it also has inner part, outer part, and even more situation is even more complicated. There are many different shear layers which are nested in one. So it's sort of a big collection of the different layers. Basically, all of them are fixed, but not all of them with Coriolis force. Ekman layer, for example, with Coriolis force, and the other layer maybe with the other force. And so, but nevertheless, eventually we will obtain the exact solution of this problem, how it's state. Let me just remind that at the moment we considering just differential rotation. And the result, you see that in the bulk of the volume, outside of the shear and boundary layer, we see only pure rotation. You see that the only phi component is working. So it's directly rotate only in the azimuthal component. Yes. And change only with cylindrical radius. So it's working azimuthal component and change only with its cylindrical radius. So this is the sort of differential rotation. Again, I stress that it's in the bulk. It's the main part of the volume of the, in this case, of the spherical shell. Of course, there are very important, even maybe more important than this simplified geophysical approximation, are the various viscous layer. And they are, some of them are very thin, some of them very complicated. And perhaps the most easiest one is the Ekman layer, to which we proceed in the next chapter. But at the moment, it seems we proceed all the chapter of this. Okay, so maybe there is some questions. Questions? Maybe somebody. Okay, please.
Can you explain again how you arrived at those boundary conditions?
Which boundary condition?
Vs equals Vz equals 0.
Vr equals 0.
Yeah, no, the last line. Last line. Vz equals 0, Vs equals 0.
Vz equals 0. Yeah. Actually, Vz equals 0, it appears that if we consider the boundary condition, you see that it depends only on f if you consider in this case the boundary condition that it's not on the inner sphere and it's not on the outer sphere, and it depends only on that, so this situation may be that only may be satisfied only in the case when it's on, because it's on the, if we consider some vertical axis and then move from the inner core to the outer core, there is two different positions, and both of them is Z component, which constitutes the air component, is equal to. More precisely the air component, but the main contribution in this geometry is coming from the Z component. So eventually Z becomes something for example. Of course, it's possible to explain it in another way, maybe more common. I hope you will do that. Okay, maybe there is one more question, or two, or three. Is there any more questions?
Now it has been reduced to two-dimensional case, or
Sorry?
it has been reduced to three-dimensional.
Yeah.
It has been reduced to two-dimensional case.
Yeah, actually it's been reduced to the two-dimensional case with arbitrary function, one dimension. It is reduced to the two-dimensional case, and it is the rule if we have the case which is two-dimensional, then the arbitrary function needs to apply one dimension work. So arbitrary function is one dimension.
That means we are getting ordinary.
Yeah, yeah. And not ordinary, simply ordinary, real answer.
Linear.
So we can very easily get them to.
No more questions. Yeah, we can take it.
Okay, let's have a small break, yeah? Okay. 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 Some missing. Oh, Maria, excuse me, Maria. Often presentation 9 should follow 10, but there is no in. Or maybe 13 is after 9. Yes, seems 13. Yeah, certain, yeah. Okay. It seems I found. Okay, thank you. Okay, could we start? Okay. Yes. Okay, let's now go further. Actually, in my previous presentation, I didn't see the exactly what is in presentation. I just finished the my presentation on the general solution, which was reduced to the one arbitrary, one-dimensional equation, dimensional function. But after that, I didn't name you the task which is necessary to solve. Somehow I already told about that task, which I ask you to do. But let's now formulate it more precisely in some sense. So the task number 1 is that perform, you can write down task number 1 to this chapter 2.4. Perform detailed transformation to obtain the dimensionless system 5 from the dimensional equation 0 and 1, provided that the variables are transformed in accordance with equation 3. Here the number of equations are without the addition that it's for 2.4 chapter. So this equation are working inside this chapter. And one more task. Carry out detailed transformation to obtain the system of 3-scalar equation 9 from the first vector equation of the geostrophic system 8. This is the second task. And actually, when I spoke to you, I also formulated the task, maybe even 2 tasks. Okay. Please explain in the detail how you got the equation 12 from the previous equations. And also the similar problem. Please explain in the detail how you got equation 14 from the previous equation again. So actually there is 2 tasks here. I added another 2. So you will be not boring. You can do something. Okay, let's proceed further. So we are now at another chapter, chapter 3, which is named Viscous Flow in Narrow Ekman Layers and Boundaries. The ambiguous representation of geostrophic flow 14, this one. Oh, I didn't put the number. Let's put 214, of course. Oh, 14, 214. The ambiguous representation of the geostrophic flow 14 from the previous section 2.3 is actually obtained by discarding in the original equation 2.5 those terms that are extremely small, provided that for this flow the length and time scales are comparable with the characteristic quantities from the section 2.2, the section which previous to this session. In uniquely defined real flow, not only these characteristic scale are present, but also singularity, smallest and smallest scale. Again, I just have to mention that we remove the term which are responsible for viscosity, and those are responsible for inertia, and but in the real situation, of course, the small scales flow, which related to this effect. And first of all, we are studying only Ekman velocity effect, because actually inertia we can completely neglect at this approach. To describe such small scale flow, it is necessary to take into account the terms proportional to the Ekman number E capital and the Rossby number epsilon, which is in initial equation 2.5, due to the fact that in the small scale part of the flow, this small number will effectively be divided into small lengths and time scales, which taken the corresponding derivatives. Okay, so this is some general preface to this chapter. Let's start from the particular paragraph of this chapter. In paragraph 1, which name flow and Ekman layers with a negligibly small Rossby number. So we neglect, now we return somehow the equation, so we neglect by Rossby number term, Rossby number and all the terms that connecting with Rossby, but keep the viscosity. So we just note that first of all, it is necessary to take into account the viscous term proportional to the Ekman number capital E, which been in form of the higher derivatives, allow us to satisfy the exact boundary condition of this 6 boundary condition from 2.5 initial system, and thus uniquely determine the flow. It's necessary to stress that the flow which we previously found is not uniquely determined. This is a problem. We can define it in a different way. But to remove this ambiguity, we should go to the account of the viscous force, because it's near the higher order derivatives. In this case, we will first discard the terms proportional to the Rossby number E epsilon in 2.5. And instead of the first equation in the system, we will have, okay, it's already written here. Now I will repeat it on the board and comment, of course. Let me remove the old stuff. Okay, the main commentary on this reduced system is that, in fact, again, we give rid of the nonlinear term. This is perhaps the most big advantage of the geostrophic approximation. So actually, removing the Rossby term, assuming that the Rossby number is not, help us a lot, because we remove the nonlinearity and we are in the linear system. This linear system is possible to solve much more easily and much more precisely than nonlinear system. But of course, then we have some difficulties now, because equation becomes sufficiently more complicated than it was initially. So this equation look not that complicated. I will write down now it. You will see that it's indeed not so much complicated, and you see it's there. But nevertheless, this system is rather simple in the vector representation. Unfortunately, we cannot solve directly the vector presentation. So eventually, we will expand this system in the corresponding coordinates, in spherical coordinates, of course, because the boundary is on the spherical boundary. And then we can manage to satisfy exact boundary condition, not approximate like we did before, and to match this geostrophic flow, very simple geostrophic flow, to the upper boundary of the viscous layer, and consequently to obtain the right solution, at least at the moment for the Ekman number. So neglecting by the Rossby number, as it's written here, we have this simplified equation. To fit more, I will start it a bit on top. So we just rearrange the term to see them more precisely. So we put the gradient of pressure on the first place. Then we have velocity vector multiplied it cross product on the unit z vector or the vertical axis. And all of this is simply equal to the E capital on the Laplacian or nabla squared of the velocity. So this constitutes the very introductory formula to this chapter, 0. The number is 0. It's also necessary to stress that this is not simply squared of nabla function. This is actually, this one is more precisely equal to the double rotor with minus sign. So it's not, indeed not scalar operator, but it's indeed vector operator. It's important to mention. If we say here we just use this part of this lambda function, lambda operator, and if there is a divergence is not, then there is no any more contribution. But if divergence is plane enforced, then we have to add to this term gradient of the divergence. Something like that. So here we have the divergence, and here the gradient of divergence. Of course, if in our case divergence is not, but in the general case, this Laplacian, of course, in the Cartesian coordinate, it's simply reduced to the scalar operator. So the second derivative of x, second derivative of y, and second derivative of z, sum up of those terms. But it's only in Cartesian coordinate. If we go to any other coordinate system, it will be very much different from the scalar operator. So it's necessary to mention. Yes. And this is thanks to the person who allowed me to understand that, or stress that maybe, understand. So the initial neglecting of the inertial term proportional to the small Rossby number epsilon is justified by the fact that if we, on the contrary, first neglect the viscous terms proportional to the small Ekman number E capital, then it will be imposed to unequally construct the flow with the remaining inertial term and satisfy all the boundary condition 2.5. From the asymptotic point of view, this corresponds to the fact that in the problem under consideration, we must first find a solution in the limit of an infinitely small Rossby number. The accuracy of such an asymptotic solution is estimated by the value of the Rossby number, which for the US core corresponds to the value of about 10 to minus 4%. So actually we just symbolically here that removing of the Rossby number is correspond to the accuracy 10 to minus 4%. So it's more than enough accuracy in our case, because usually the most of the estimation are very often just an order of magnitude. So here we are quite safe working in this limit. And of course, omitting all the linear term. The effect at viscosity should primarily be felt near the spherical boundary of the liquid core of the planet under consideration. Okay. Oh no. Okay. Okay, so it's again the reference on the picture you saw many times. I will not repeat it and find, but nevertheless you see that the configuration of the planetary layer. So therefore the natural coordinate system, again a reference for the initial system, with the first equation replaced by the zero equation, with this one, will be a spherical coordinate system. Let us write all this equation and boundary condition in detail for their further use in this section. So let us start with the equation 0. Let's start the equation 0. The spherical component of this equation are determined by the scalar multiplication by the corresponding unit vector. For more details, see problem 3.1 below. Here we also state the problem. As a result, for the three components of equation 0, we obtain the system. Let's comment and write down this general system. As I already told to you, if we proceed to the detailed representation from the vector representation, of course we can get much more lengthy equation, very much more. So we just start from this equation, and pressure is in the first place because it's the most important term, and may be of equally importance or maybe greater even, but at least comparable with the pressure is the Coriolis term. So we start from them. And again, as I already told you, that the Ekman number are in front of the Laplacian, but not ordinary Laplacian, but the vector Laplacian. And it has a very tricky form, especially in the spherical coordinate system. So we just, let's write down and comment every term of this equation. First of all, we of course expand P. And here we simply take for the r coordinate, for the spherical radius r, just dp by dr. Then component of the radial, let's stress here that this is gradient r component. So gradient r is the unit radial vector in radial direction, as I like. So then we start with the Coriolis force. It's important to understand that the Coriolis force in the radial direction is corresponding to the to the velocity component, which is in phi direction. Again, we have this rule of the cross, that for such a complicated term, which are coming from the cross product, there is some sort of the cross. So we have the R component, which is going from the V phi direction. So this is the shows the tricky way of the rather tricky way of the Coriolis force, that it's not acting directly, but somehow in the cross it's twist, and actually twist everything. So why we expand it like that? Of course, we use obvious expansion. And then a bit more complicated nature is, of course, we keep E capital, which is the Ekman number. Then we have rather lengthy equation. I don't know if I am here. Okay, but I will try. So, of course, first of all, we have just scalar Laplacian. Let me to stress the difference between scalar and non-scalar. Here put not square of the nabla function, but the just lambda function, just to stress that it's vector. Okay, so but for the first component, of course, we have scalar Laplacian, and for the R. And again, you see that in the case when we effectively have not cross, because we have the double cross actually here, but double cross somehow cancel each other. So after one cross, we have sort of the twisted nature of all the flow, all the everything that appear here. But if we act twice, then crosses somehow cancel each other, and we have a sort of the symmetric nature. So we are actually working on the R component, and the major component is appear here like that, because it's somehow symmetric representation. But of course, there is some traces of the spherical coordinate system. The most simple one is like that. Then there is even contribution of the other component of the velocity, or other component of the velocity, which is constituted in this way. Theta. Here we have a lot of signs. Theta. And finally, of course, we have only also third component. In every component, we have all three of them. But on the top, of course, the component which somehow symmetrical, which is produced from the initial value. And the final azimuthal component here is GVP. Okay, I fit it by GV. And it's interesting just to stress here that when we involve another component of the velocity, again there is some symmetry. The theta component, we taking the partial derivatives with theta as well. And phi component, we taking the partial derivative with phi. So there is some symmetry everywhere. Let's proceed further to the theta component, which is, of course, here we have involved Lamé coefficient, which is for this component is just R. And about the Coriolis force here, we have again okay. Okay, what is written in my notes? But I'm afraid that there is a mistake here. I'm afraid that I'm mistaken because it's repeats that one. Definitely it should be the, as far as I see, perhaps not theta, perhaps R. I don't know. Okay, please check that term. Just expanding by rotor. I'm not sure that it was written correct. But hopefully the rest is correct. So again we have scalar nabla operator or double or the nabla squared, and it's again include, first of all it's include theta component, of course. Then it's include again radial component, because it's even prevail for the break this sort of symmetry rule, but maybe not so much. 2 over r square dv d theta d theta. But nevertheless, we have the theta component. It's sort of the mixture. Then we gain theta component like that, and divided by r squared minus theta squared. And finally, we have phi component. To cosine theta r squared sinus squared theta. It's a bit complicated. D phi. D phi. Okay, now we can number this formula. 3.1. Maybe that's correct. Yeah, perhaps it's correct. Maybe I just afraid, but please make sure nevertheless. I think that it's correct, but and the major contribution is actually here. The most important contribution is in the phi direction, and here we have coefficient Lamé r sine theta, so it's walking like that, r sine theta and dp by dphi. And here we have sort of the major contribution to the Coriolis force, which constitute with two terms. Here we have only one terms for this component, but for the phi component we have two terms in the Coriolis force, which is in the spherical system, and both are quite important. So we have 2 cosine theta b theta And I just write here to fit it in this place. Then plus 2 sine theta, where again we see this cross rule here. We have where and sin theta and v theta, maybe not so precisely cross rule, but nevertheless here the corollary term work like that. And eventually we again have, of course, again we have square on tabla on v phi, and then we have plus theta. Oh, sorry. Sorry. dvr by d phi and plus 2 cosine theta quadrat sine quadrat theta dv theta by d phi and the final term is just v phi without any derivatives s quadrat sine. Okay, seems I didn't mistake anywhere. Okay, so this is actually the consequences of Navier-Stokes equation, where we neglect by Rossby term or all nonlinear term, and it's in the spherical system. It's quite lengthy. Okay. Okay, so here it's have 2 pages, so you can just write it down if you didn't write something not before that, so you can write it down. Okay, so we need divergence as well, of course. Why not to use the divergence? And necessary to stress that here this Laplacian operator is again in spherical coordinate system. It's not that simple like in the Cartesian coordinate system. So it was to write down all this Laplacian in spherical system coordinate. I mean, but it's not exactly Laplacian for the whole equation. It's only for the part of the Laplacian. It's necessary to stress. But nevertheless, this Laplacian is exactly correspond to the corresponding spherical Laplacian, or maybe more precisely a delta function. So actually, by definition, we have that this expression which used here is by definition just the product of 2 Laplacian, so it becomes scalar product, because actually every nabla is sort of the vector. If we multiply it scalar on itself, it will be scalar. And this scalar is in spherical coordinate system, can be represented. No, it's not shown here. Yeah, it's shown here. Let's write down here, it's at will. One over r square. Again, I stress that here coefficient Lamé is equal unity for the radial component. But when we have double nabla operator, we should operate with remaining Lamé terms. We should multiply them, here multiply and here divide. So eventually we are getting this term like that. It's important that here we have R square, and it's in some solution it becomes rather important. So we have double R operator, which work like that. Then we have again coefficient Lamé for this is R, but we should take into account other coefficient of Lamé. And here an important addition, that sign is appear here. And the most maybe simple form is for the phi component. It's just multiplication of the all Lamé coefficient squared. And double derivatives, partial derivatives of phi. Okay, this is another formula, 3.2. Oh, no, it's without numbers, sorry. It just actually explanational formula, which it's not dissolve the number. Okay, so let's proceed. The real formula and the last formula, which formally constitutes the system of equation for this problem, is of course divergence free, and it's written here. Let's write down and comment it's here as well. So we have again the display with Lamé coefficient, and it's now very similar to that one, you see. We are taking the partial derivatives of R squared VR. And it's interesting that from these derivatives we have such interesting dependence like proportional to the inverse power of R, which we usually when we expand the equation. Because basically there are many contributions where we first of all take into account radial component. And for the theta component, of course, we have R sine theta. Again, multiplication of the Lamé coefficient, not square because it's like here, it was here. But the derivative is against sinus theta, very similar one, and also very symmetric because the theta component we are taking partial derivative as theta as well. And for the same rule is plain for the phi component, azimuthal rotational component. We have an r sin theta, the same as here, and then we have derivatives of v phi over d phi. So this is dissolve the special number 3.2. This is divergence condition written in the spherical system coordinate. So the system of equation 1 and 2, actually this one and this one, is finally closed by the boundary condition from 2.5 from the general system, which in the spherical coordinate system under consideration are described in detail as, there is still some place, hopefully I fit it there. So it's after all this dimensionalization, which will take place here, we have in a rather simple form. So at R equals C, so on the outer actually boundary, which rotate with the mantle in case of the Earth, or maybe to the outer mantle for the other planets, or anyhow to the outer boundary layer. So at R equals C, as again I just mentioned that it's for the Earth case, this C is about 3. So first of all, we have that the radial component of the velocity is not. We already discussed it because it cannot penetrate. Then, because our coordinate system is directly related to this mantle, on the boundary of which we are formulate this boundary condition, so theta component is also not at this point. And also, of course, a phi component is also not. Because it should be exactly the same boundary condition as the mantle is rotating in our coordinate system. So the boundary condition is just 0 everywhere. And at the inner boundary, situation is slightly different because we suppose that the inner boundary is rotated with slightly another angular velocity. So of course the first two terms are the same. I just show it like that to make things clear that it's exactly the same. Also, radial component of the velocity is 0, theta component of the velocity is 0, and here, okay, maybe. Okay, this is constitute. Oh, it's even written in Russian. Okay, so at this Russian pre means that at R equals C, and this pre is also at R equals 1. At least have some fun in Russian language. Okay, and the most important component, which actually drive all the solution, that V phi. And because we chose as unity the radius of the inner core, so this V phi is simply sine theta. With this scaling, which we adopt before that, so the system is very much simplified. Actually, it's important to note that this system at the moment has only one parameter. So it's just one parameter system, so it's a very big achievement. So this is its own formula, of course. (3.3) very symmetrical formula. While the boundary conditions are quite antisymmetric because there is 0 everywhere on one boundary and there is some differential rotation imposed on another boundary. Okay. Let us quality analyze the obtained system 1, 3 here. 1, 2, 3. So this is complete system, which you constitute all the condition, everything. Let us qualitatively analyze the obtained system 1, 3 in order to identify in its small viscous scale that determine the flow near the boundary. To do this, we will select in equation 1 the terms with the inertial Coriolis force and the term with the viscous force. So initial Coriolis force I already told you, this is this term, which consists one term. Here there is other term, also consists the similar term. And there is also maybe the most important one on the phi direction, which consists two terms, Coriolis force. And if we consider in terms of viscous force, this is very lengthy stuff. But here we should take into account the highest derivative, because we suppose that this thing is working in thin layer. So if we divide it on the characteristic thickness of the thin layer, some layers becomes, some of the terms becomes more important, and other not so important, because first of all we are looking in the radial direction how it's work. You immediately could see that all these terms which are outside here are not so important like this first, because it constitutes second derivative, and namely in radial direction, which is important near the boundary and make this small very thin boundary layer. And the effectively differentiation is in a radial coordinate system is effective actually in this case in the r direction. So if we take the higher order derivatives, namely in r direction, so frankly speaking, here we have derivatives in another variable, and here we have derivatives. Of course, it's somehow hidden here. It appears from here. Yes, but nevertheless, it's derivatives of the second order in r direction. So many, not simply it's more important. It's many order of importance, because here we have actually derivatives of order of 1, and here this is the order of magnitude of all these derivatives should be divided, should be as we take the small thickness of the layer, divided some one on this small thickness, and then put in square. So it will be very important term if we consider it's radial, but all the other terms are not problem. Let me summarize it somehow. The term describing the Coriolis force are in the left-hand parts of equation 1 I just showed you. And the terms with the hands and are directly proportional to one of the velocity v component, and here to these two components. The terms describing the viscosity are in the right-hand parts and are proportional to extremely small Ekman number. So from one point of view, it's proportional to extremely small number, but from another point of view, it's proportional to the extremely larger term which is connected with the second order derivatives in r direction as in our case. So the term describing the viscosity are in the right-hand part and are proportional to the extremely small Ekman number. Therefore, the corresponding viscous interaction can be neglected, whereas the scale of the flow is comparable to unity. So this is the maybe main message. Whereas the scale of the flow is comparable of the unity, we can use the simple geostrophic approximation which I showed you in the previous lecture. And here we can neglect by this small Ekman number term. However, therefore, the corresponding viscous interaction can be neglected, again I stress that, whereas the scale of the flow is comparable to unity. The presence of small scales of the flow at the boundary will, first of all, lead to the fact that the square of the small scale, let's note it like, oh no, it's okay. Scale. So let's suppose that the scale is small, and the thickness of this small scale is proportional to the delta. So the corresponding the presence of small scale of the flow at the boundary will first of all lead to the fact that the square of this small scale, theta square, will effectively manifest itself in the denominator of corresponding radial derivatives from Laplacian operator in the right-hand side of 1. So it's the same as I told to you. So if we have delta square, so from this Laplacian operator, especially from this term, we should stress from this term, which is against the radius, it's even becomes theta square. So very roughly, to make some balance, to reach the balance between this Coriolis term and pressure term, of course, and this viscous term, we should very roughly, of course, reach a balance that square of thickness of the boundary layer is about the Ekman number. So in this case, you see that if the thickness of the boundary layer which coming from this place, and you see that here we have the radial derivatives. So this is number it as formula 1, 3, 4. It's a rather important formula that we balance in the way that to reach this equality. Then you see, if you consider any term of this in order of magnitude, then you see that here we have Ekman number, and here we are divided by delta number. And if they are comparable, so we eventually get in here the term which is constitute like that. We take the epsilon capital, and effectively, when we are taking the radial derivatives, and double radial derivatives actually, we are in effect that delta is squared here. And to reach the balance, actually to reach the balance between this term and this term, we can, of course, the state the same actually as it was stated here, that its value is of 41. So in some sense, we are getting the qualitative picture how these things are working. So we just see that there is the Ekman number, and to put it in game, that allow to coincide with the Coriolis number, with the pressure number term, we should manage with the thin boundary layer. And it's this thin boundary layer even has its own name, of course, Ekman boundary layer, and due to the person who invented it actually, from this consideration. So therefore, the corresponding viscous interaction can be neglected, whereas the scale of the flow is comparable to unity. The presence of small scale of the flow at the boundary will first of all lead to the fact that the square of the small scale manifests itself in the denominator, as already shown in denominator. Here, denominator. Of the corresponding radial derivative from the Laplacian operator in the right-hand side of here. This corresponding Laplacian, and of course we take only the radial component, which is the most important. Accordingly, if we require that the viscous force and Coriolis force balance each other, then we get. Okay, I repeat it second time a little bit in other words, just for you to understand how these things working. Hopefully you understand. So thus, the main asymptotic parameter determining the viscous flow in narrow boundary layers of thickness of the order of will be the square root of the number of delta. And so actually we see that from this relation, of course it's a crude relation, but nevertheless we can for the estimate just write down from this estimation that the delta thickness of the boundary layer is E to which power? Can you say to which power? Half, yeah, exactly. So just 1/2. Yeah. And this is precisely the thickness of the boundary layer. My congratulations. You understand how this thing is working and how this, namely, this 1/2 is appear and show that it's working well. Okay. How many time we spent? I didn't count. How many time we spent on this till this moment? Huh? 1 hour already? Oh, okay, let's have break. Maybe just a small break, yes? Rani? Yeah, small break. I will just sit down for a minute. Okay. Let's conclude the previous chapter. This conclusion is that it's working. Okay. Thus, the main asymptotic parameter determines the viscous flow in narrow boundary layers of thickness of water of this e to the 1/2 will be the square root of the number. So actually, I already wrote this, maybe one of the most important summary of this previous paragraph. Let's now start at this next paragraph in chapter 3, second paragraph, which is named as asymptotic expansion in a root of the Ekman number. So actually we found the small parameter here, and this small parameter, it's necessary to stress that effectively it's not Ekman number, but Ekman number to the half, because namely this small parameter is working on some distance. So we should scale somehow the distance with this parameter, and then to see to which equation it's lead. So we will search a solution in the form. Quite good parameter, why not to use it? Moreover, its problem is very simple in the sense that it actually has only one parameter. So we reduce it, it's a lot. In order to find the type of expansion in the terms of a small parameter, it is selected so that the main terms are balanced. This expansion usually has a standard form. So this is quite a standard form. I will write to you all this small parameter expansion usually work in this standard form. The only not so standard thing here in this expansion that this small parameter is enter near the higher orders derivative. So this, of course, allow us to take it into account and properly to expand every stuff that we have. But nevertheless, to my recollection, pick up the Ekman boundary layer parameter near the higher order derivatives is perhaps the most simple one, because very often if we have small parameter against the higher order derivatives, we not simply use this expansion, but usually in expansion there is some sort of jump term or whatever you name it, like in WKBG solution. All of this stuff will appear later, we'll show it. But in the simplest scale, like a Ekman boundary layer, this expansion is quite simple and it's quite straightforward. Actually, for this somehow singularity system, because it's singular or in the sense that there is a very small scale against the ordinary scale, and there are very small scales. So this is sort of the singularity. But this singularity, which is developed for the Ekman boundary layer, perhaps one of the most easily treated singularities. So I will show you right now how it works, but first we will show the expansion, and this expansion I will show you and comment, of course, how it works. After, when I remove all the stuff from the blackboard. Okay. So rather standard approach, we will search a solution in form of the expansion in terms of a small parameter delta equal, delta equal square root of Ekman number. This is our small parameter. Just should stress it. Small parameter. Since this parameter has a clear physical meaning, I'm just repeating, as a thickness of the viscous boundary layer. And so we expand in the standard form using this smallness. And so we expand very simple. We just take velocity field, initial velocity field, then we expand it to the zero order. At zero order, we just suppose that there is zero at this expansion parameter, and correspondingly V0 approximation. Then the next, in quite similar fashion, we have plus in the first order. Of course, we cannot write that, but nevertheless, just to stress the method, how it works, let's put one here. And this, of course, corresponds to V1, vector of V1. And of course, there are another terms, but as far as I told to you that if Ekman number is for real reverse molecular value is 10 to minus 15, then we could neglect very freely the terms of order delta squared, which is in fact is equal. Maybe not equal, but in order of magnitude, better to say. That is in order of magnitude a Ekman number. So 10 to minus 15, of course, we can neglect. So for us, it's more than enough, these two terms. And the similar expansion is in pressure, of course. Again, we put zero order pressure here, then first order approximation here, and plus some value which is of order delta squared. So this constitutes the formula 3.5. So here the order of magnitude and of the delta is square are such a term which are smaller than actually Ekman number, because square of this delta is about the Ekman number. So in order of magnitude to the first term, main term. Such small terms can be confidently neglected, since for the Earth it's at least less than 10 to minus 8. For the Earth it's 10, this Ekman number is less, even 10 to minus 8. But it's for turbulent value, this upper bound. But for it's turbulent. While for the real molecular value, it's 10 to minus 15, as already told. Molecular value. So we are quite safe to remove that. Moreover, in the expansion 5, even terms of order or of delta can be neglected. Moreover, so even this term, which is the first order, of course we can calculate it, but even it has the value, even if we consider turbulent case, it's 10 to minus 4, so even it is not so important. So this our primary goal, just to find the zero order term, and more precisely to say that it's not zero order, because actually when we operate with this small delta expansion, of course we involve it as the inverse combination in the equation I previously showed to you. So it becomes rather important, and term compared with the other term like a Coriolis and pressure force. So thus to describe the flow, it is quite sufficient for us to find in one which okay here as well. Okay. It was in previous lecture. Okay, but nevertheless, just believe that in one it was such a system. So the main terms of the expansion V naught and P naught, which are of the order of unity, or otherwise actually we have this or zero, this is of order unity, of course, and this is namely the term we are looking for. So, and further, we will omit this index 0 everywhere, since we will limit ourselves only to the main terms. If we limit ourselves only to the main term, but it's maybe more than enough, because even in the worst case of the Earth, it's 10 to minus 4 accuracy, more than enough. So it's just very good accuracy. So further, when we consider all this stuff, we will take into account this only first term, and it will be enough for our purposes. And to make this thing simply, we just remove the zero, subscribed this zero index from here and from here, and work with this field. So since the solution we are looking for must be strongly concentrated at a distance delta in the radial direction near the boundary, in the boundary layer, it is quite reasonable to assume that taking the derivatives with respect to the radius increases the determinable function by a value inverse to the small scale. So formally, when we are taking some derivatives of R in R direction, in the boundary layer, of course, near the boundary layer and at the boundary layer itself, so it will be of order of magnitude, of course, roughly. of 1 over delta. And this is much more than unity. And it's, of course, compensated to the viscous force. Therefore, it is reasonable to introduce, instead of radial variable, you see that actually we should scale with this delta, which is actually equal to the 1/2. Since the solution we are looking for must be strongly concentrated at a small distance delta in the radial direction near the boundaries in the boundary layer, it is quite reasonable to assume that the taken derivatives with respect to radius increase the differentiable function by a value inverse to the small scale, or other words, as I wrote here informally. Therefore, it is reasonable to introduce instead of the radial variable a radial stretched variable, somehow stretched on this all this stuff. So we introduce stretched variable sigma to stretch a radial stretched variable in the outer and in a boundary layer, which is in accordance with 4 can be identified as, let's go to the next slide, which can be identified as following. So we see that this is different variable which we explore near the outer boundary and near the inner boundary. So we just make the indexes here at the outer boundary. By definition, of course, we make this stretched variable like that. So we have radius very close to the radius of the outer boundary, which is 3, as I just remember, in the square. And so we just divided it on the delta. So it's at the outer boundary. At the outer boundary, when module, so there is, in mathematicians there is such a vertical line that means that under condition, something like that. So under condition that r minus c, module of r minus c, is of order of magnitude as delta. So close in the boundary layer. And also we can introduce at the inner layer in the same fashion also sigma. Now with index I, because this is the inner core. And here obviously we expanded like. Here it's necessary to mention that R is coming in the first place. R is coming in the first place because okay, no, doesn't matter. So here we have expansion in this way, but here we have expansion in this way. R minus 1 over the delta, obviously, because the inner radius is here set to 1. So again, the similar condition of existence of this boundary layer is that the module of R minus 1 is of order delta. So this is inside this boundary layer. So it constitutes the formula 3.6. So this is stretched variable, which we put here. And here the external variable theta O has a magnitude of the order of unity. So you just, under this condition, under this and this condition, you see that this variable, this stretched variable, becomes of order unity. And here it becomes of order unity when we're in this boundary layer. In the outer boundary layer and the internal stretched variable, theta E, has a magnitude responsible to that of order 1 in the inner boundary layer. Outside the boundary layer, both of these stretched variables becomes very larger in magnitude. And of course, we cannot lose them well outside of the boundary layer, only in the boundary layer. And we now substitute the solution in the form of expansion 5 into 1, 2, and using the stretched variable 6, we isolate the leading terms of the expansion. See the index 0, which we omit actually. So again, just saying that I omit the index 0 because we only the first term taken into account. So near the rigid spherical boundary, or in other words, inside the each Ekman boundary layer. Formally, this is done by equating similar term at the highest power of the asymptotic expansion in formally can be done in the asymptotic expansion with the parameter delta equal square root of Ekman. Consequently, for the leading terms of the system of equation 1, 2, it's difficult to return to this equation, but hopefully you can see on your notes. And so the final result looks like this. The final result is possible to write down. So as far as maybe you remember when I considered this very lengthy equation, I stressed your attention on that only the Laplacian, double Laplacian, no, just Laplacian and the double nabla term is important. And moreover, in this double nabla term, only radial term is important because all the other terms are vanishing. So eventually we get very simple system for this boundary layer. Here, of course, we have gradient P. Then we have Coriolis force, which is look like that. So this is the vector cross product of the velocity on the unit vector in the direction of axis of rotation, which is has a coordinate z. So this is, of course, doesn't change anything. But very importantly, that on the right-hand side, we have plenty of stuff on the right-hand side, if you remember, especially this very lengthy now double square nabla term. But only the radial derivative is important in this term. Moreover, the second radial derivative. If you remember, this second radial derivatives appear. There is, of course, the first radial derivatives, but nevertheless, the second order radial derivative overcome everything, and even first order derivatives. So it's still 10 to minus 4 accuracy, and eventually even less if we consider the molecular value 10 to minus 8. 10 to minus 8, 10 to minus 7, anyhow, it's quite more than enough. So we keep only one term. It's a wonderful message that we have only one term here. And this, see? I didn't mark the indexes here because it's the same for this boundary and for this boundary. So I just put the universal here, but of course it's presumed that it's in fact has index E or O. For different position, of course, for one boundary layer and for another boundary layer. And of course the divergence is equal naught. So it constitutes the system 3.7. So here the stretched variable xi is not indexed because the form of this system of equation 7 remains the same in both the outer and any Ekman boundary layer. Okay, so we finished this paragraph, and then we proceed to the next paragraph of this description of the Ekman layer, and then we have a lot of things to do. While this formula is very simple, nevertheless, its manifestation requires some additional efforts. Oh, sorry. Okay. Oh, perhaps I should switch to another PowerPoint presentation. Sorry. Okay. 16. So let's start this next chapter. No, not chapter, paragraph. Chapter is bigger and paragraph is much more smaller. So the geostrophic flow 214, which was shown in the previous chapter, obtained in the previous chapter 2, will obviously satisfy equation 7. So it's interesting that this geostrophic flow is obviously satisfies this equation 7. Through the regular or other geostrophic path and the singular or boundary path in the form. So here the singular path appear anyhow, but maybe in so relatively simple expression. So we can choose the form for the velocity field, which is rather natural here. So we just expand it like v theta. And it's necessary to stress that this v theta component is changed only in direction of theta and xi, this expanded variable, and multiplied it by the unit vector in theta direction, of course, which I wrote down in my lovely form of gradients. And there is, as I already told you, another component of the velocity, because you know that due to the non-penetration condition, we cannot consider here the r component of the velocity, because it should vanish. And in this very small boundary layer, from the r component, we only later involve the derivatives. But if we consider the general representation at the start, this r component is just absent. And there is no r dependence for the theta component, because it's a very thin boundary layer, so we should not take into account radial dependence of theta component. And the same trick is for the phi component. This phi component I will write down slightly different from it, just to understand better. Here there is a contribution of some, at the moment, arbitrary function, but we defined it later, which depend only, again, not depend on the radius, but depend on this stretched variable. and all this. Then we have this geostrophic flow in order to satisfy the geostrophic solution. And as was already we told and showed to you, that this depends only on cylindrical radius. And the spherical coordinate system, this cylindrical radius is r sine theta. So we just close that and put here the unit vector in the direction of phi. So it's constitute from formula 3.8. And it's necessary to stress that here u from us, s, this s actually, this is cylindrical radius, s. U from s is the derivative of the free pressure function divided in 214. So if you remember that everything was defined via the pressure. So for geostrophic flow, and as already told, this S is actually r sine theta. So this r sine theta is the distance from the rotational axis of the cylindrical or otherwise cylindrical radius. The pure single function u and v theta, this pure single function, singular function, u and c theta, why they are singular? Because they involve this stretched variable. So this stretched variable, and this is the sort of the singular function, which concentrated in the boundary layer. But outside the boundary layer, it just vanished, and very quickly. So they should be significant only in the narrow viscous layer near the boundary. Outside this layer, the singular function should decrease so much that neglecting the viscous component in 7 and completely switching to a purely geostrophic flow US. So it's not the accident that we chose this function in this way. So you see that if it's going much less than c, this radial, so it's become negative and just tend to the very small value and eventually vanished and rest only on this geostrophic flow. And the similar situation is for the boundary which is here. So, of course, we from the singular velocity from 8, this singular velocity from the formula 8, it is sufficient to consider both angular component of the vector equation from 7 and 1. From 7 and 1, it was the initial system, actually. Taking into account the geostrophic equation, so of course we also will take into account the geostrophic equation. I will not repeat it, but nevertheless we should meant that again I stress that if we outside the boundary layer, we remove all this boundary layer solution, but and formation, and the geostrophic flow remains, which depend only on the cylindrical radius. So to obtain the equation, determine the singularity velocity from 8, it is sufficient to consider both angular component of the vector equation from 7 and 1, taking into account the geostrophic equation and the fact that the angular part of the singular pressure gradient is negligibly small. It's important here it's also to stress that not only R component is small in the boundary layer, but also the derivatives which are not radial derivatives of the pressure, they are also small, because you know that when we are taking the derivatives against the radial spherical radius, especially in the boundary layer, then we have the small value divided on the, effectively we divide the change of the pressure on some small value. So the radial component of the pressure, I mean radial in common sense, because pressure is actually gradient of P. And so the radial part of this gradient is important, but the other is not important at all. We can neglect them everywhere. Did you start? Okay, thanks you. Okay, so let's on my lecture end, I got the impression that perhaps this the derivation of the equation and the solution in the boundary layer was not fully understood. So I think that it was to briefly, very briefly, to remind how it works. And after that, we also will consider in the detail the task, which allow us to better to understand. So I am somehow return to the equation 3.8, which is shown here. I will show just in PowerPoint presentation. And the extrophic flow obtained in the previous chapter 2 will obviously satisfy equation 7, from which the derivative with respect to the sketched variable theta is completely eliminated. Therefore, we represent the flow velocity in equation 7 through the regular or other geostrophic part and the singular or boundary part in the form. Let me explain how this thing is working. Oh, I don't see. Okay, so first of all, on the radial direction, we are taking into account theta component and xi component. And we also considered axisymmetrical situation when there is no dependence on phi. So actually, it allows us to simplify further this approximation. And also, there is only two components of the flow. One of them is which is directed in the direction of theta function, and other is which is directed in the azimuthal function direction. This is actually due to the fact that we have almost no contribution in the radial direction. So there is no contribution in the radial direction. But here we have a very clear phi contribution, which is in the azimuthal direction. And this contribution constitutes two parts. One part is the regular geostrophic flow, which we could reach. This one I show the mouse. This is the regular geostrophic flow, which we should reach when we are outside the boundary layer. And this is another, so it's in some sense supposed to be known. And here we have another part which we will be calculating dependence on, to which our flow will be under condition that its geostrophical part is completely absent, and in excess that there is corresponding boundary condition are satisfied here. So we have only two components in theta direction and in phi direction. There is no component in r direction. But more precisely to say, there are some components in r direction. In fact, but it's singular component. It's working only in the boundary layer and working, maybe possible to say somehow sharply, very sharply this zeta is working. How it's working, let's see on another slide. So to obtain the equation determining the singular velocity from 8, it is sufficient to consider both angular component of the vector equation from 7 and 1, taking into account the geostrophic equation 2.8 and 2.14, and the fact that the angular part of the singular pressure gradient is negligible. As a result, we obtain. So actually, again, I stress this simple result appear only because for the Coriolis force, we have no component. For the Coriolis force, we have component only at the geostrophic flow and also at the Coriolis force. And from the geostrophic flow, there is also no component here, but there is a component which depends on this theta things, which is doing very sharply. And this one, again, also the same. So we have the component of the velocity which we obtained from the previous equation. And here there is a very simple equation. We can solve it with the boundary condition. Boundary condition is that theta component is not at the boundary of the outer boundary. Here there is very specific boundary condition. If you remember, we this term specify in this way. So it at the boundary, this complete term, small u plus capital U, should be equal 0, or otherwise it's there is a sort of the cancellation of the geostrophic flow U directly on this boundary at R equals C. And also there is at the same boundary, at another boundary, it's at one boundary, and if we consider another boundary, here we have a little bit another situation. At least in C component it's the same actually, this situation, but on this component here we have again this effect of the geostrophic flow, but also there are some differential rotation, and we can understand this boundary condition by just rearranging this capital U to this side. Then we have the sum of the small u and capital U, and it's exactly what we assume in the initial flow. You see that here there is a u, small u and capital U. So we are setting out this boundary condition, and the problem is quite simple actually, because it's this the ordinary linear equation in respect of theta, in respect of xi, sorry, in respect of xi. So this xi is quite ordinary, and we can use it like that. So for it's sort of the classic things for this condition that this small u which we are looking for and this component, theta component of the velocity, are all proportional to the exponent of some eigenvalue lambda times this z component. And so actually eventually we have this representation, whereas there is a component which depend on the could depend, actually not depend, but could depend on the various value of lambda. And so also there is the exponential part, and this xi component. I just remind you that this xi is actually the ratio of the difference between the actual r from the boundary, so it's actually small value, and you divide is by the square root from the Ekman number, which is also small value. So this small value are both compensated in the boundary layer, but if we are going outside the boundary layer, then we actually have that outside the boundary layer, this work in the opposite direction. It's not compensated, but it becomes to diminish. Of course, to reach so, we should impose the proper lambda coefficient, and to find it what is it working for and what is it given for us. So actually, then we are resolving the characteristic equation. In this characteristic equation takes the form, and it's important to know that at the moment this theta, we are not resolving again this theta component. It's play while it's coordinate, but it's not playing the role because there is no derivatives in theta, and so so it's plays sort of the parameter. So we just can regard this system like the system with the parameter theta. So we eventually, because the derivatives are only in respect to the radial derivatives, which effectively stretch it out, that it's concentrated near in the boundary layer. And the same situation is for the with the second equation of this type. So eventually, it's obviously that from these two equations, we have characteristic equation, which is written here like that. So, and it's a fourth order equation, as you can see. Therefore, we can, an alternative approach to find a solution to equation 9 is to exclude the singular differential rotation u from it, and then we immediately obtain a single equation. So this we obtain this single equation. So previously we just solved two equations, each of them of second order. But there is also a more simple way, maybe which we choose, that we are putting one equation into another equation, and so eventually we are getting fourth order equation. And this fourth order equation, of course, has a solution with characteristic equation which look like that and determine this lambda stuff. And it has two sign, plus minus sign and plus minus sign. So for finally it's constitute four solution, and for different full number. So we are very much could involved in this stuff, and so eventually, finally, the solution for latitudinal component of singular flow can be written in this form. And you see that just in one form, we merge together the boundary layer which is outside and the boundary layer which is inside. But the chosen this lambda coefficient we put here for the real part, of course, of all this situation, because there is an imaginary part, but we don't interested by the imaginal part, but we are working only with the real part. This real part, you see that there is a plus here, and with this plus sign, how we define this xi o, this xi o allow us to diminish this term, all this term, when we are well outside from the boundary layer, just because this is exponential dependence and it's divided by the small e number. And so if we are going sufficiently away, even not so much sufficiently, we can, for example, move just 1.10, less than 1%, and it's already more bigger terms come and forth, and they will produce a diminishing of this structure which is inherited from the boundary. And the same play is here, but I should stress that here there is minus sign, just because this component of the stretched variable was defined in the same way as here, but if from this outer layer we are going outside the layer, we should go in the direction of the smaller r. But here, to go outside from the boundary layer, we should go in the direction of the larger r, because this is the inner boundary. So from the inner boundary, we should go up with rising of the r. And while here we should go with diminishing of the r. So if we go from the outer boundary, then we go this way. So eventually it appears that there is a different sign, and it's possible to do because we have even 4 different signs. So this combination of two will show the overall. Here you see that in this way we can get the formal representation. And also it's interesting to stress that this formal representation is dependent on some sort of the free function which are here written. There is 2 free functions which we will use further to satisfy the shear layer condition. And but anyhow it will satisfy to the boundary condition. And because it's one unique equation for the v theta, but for the another component which is actually working in the phi direction, azimuthal direction, we should just take the second derivatives of the theta and we get the exact equation for the this phi component. Azimuthal component, other words. Or maybe more precisely to say that it's not complete of azimuthal component, but this is just excess over the geostrophic flow. Because as I showed you in the previous slide, we have this representation. There is geostrophic flow and there is this function we are looking for. And so eventually this function is working in the way that it's cancel the geostrophic flow on the boundary, while this function itself removed from the boundary layer structure, and we have only geostrophic flow outside the boundary layer. So in this sense, we are perfectly matching the boundary layer and geostrophic flow. Okay, so it seems I repeat, I hope that maybe this point is a little bit better clear. But to the next part of this lecture, to proceed to the next part of this lecture, I think that it will be good to name you some task which is possible. Okay, maybe now I should set another PDF file, sorry. I'll do that. This one 17. This one 18. Oh no, there is no. Okay, so unfortunately there is no presentation about this task, so I will write down here about this task. Okay, but for the reference we should keep this equation to which we will return in some place, at least this one, and then we see what else. So actually we are close this chapter, but nevertheless there are some important tasks which some of them we explain in the detail, and another of them you just please write down. I dictate to you and you just write down for you. So exercises for chapter 3. 3.4.1 task. So please write down. Carry out in detail all the transformations necessary to obtain the scalar system 1 from the vector equation 0. You remember that it was the equation 0 from which we started this chapter, and after that it was equation 1. So your task is carry out in detail all the transformation necessary to obtain the scalar system 1 from the equation 0. So there is some example how to do so you can just also write it down. For example, the radial component of the Coriolis force is found by multiplying it by the unit vector grad r, or other words, yeah, sure. I'll show that. Okay, so for example, the radial found by multiplying it by the unit vector gradient R. So we are doing such an operation. For example, 2v multiplied it by grad z, and then we want to get the radial component of this. So there is the vector multiplier of the here. To get the radial component, we simply scalarly multiply over the grad R. So then we will proceed like this way. Now I'm only speaking about radial component of the Coriolis force. So you know that there is a dot value and the cross value with the vector quantities, and you can exchange them. It's a very important rule which is very often used, and in this situation it's quite usable to exchange these two, and it's changed nothing. This is, I don't know how this rule name in English, but in Russia we say that we can exchange dot and cross, something like that. So actually, to get the corresponding value of the radial component of the Coriolis force, you are working like that. You keep this and you put dot here. So consequently, you have grad z multiplied by grad r here, and dot is here. Just to make it absolutely clear, let's do like that. So then we just expand this vector product on the corresponding gradient and multiply them. So we have 2v vector, which is, okay, let's, for definition, make more brackets. And so from this one part, you know that the z is r cosine theta. You know that. It's just by definition. So we, after acting gradient on r cosine theta, we obviously obtain cosine theta gradient r. Then here with positive sign, we take the gradient. Gradient is just cosine theta of this value. And so, and it's also multiplied by the unit vector in the radial direction. Then we take the gradient of the cosine theta, which is again the theta. So it will be minus sine theta. So it would be minus sine theta, and here we have, and here we should have this next part of the unit vector, and here it could be written like r grad theta. This is all this is unit vector. Okay, so finally we should just multiply by grad r, which we keep from here. So eventually, after all the identical transformation, which we have here, this stuff is cancelled, this stuff will remain, and so eventually, I will maybe even write here on the top the final result. So we How for radial component sinus theta v phi. So, and this in the same fashion we can expand Coriolis term in the same manner like we did here. Then let's. So, should I remember? Do you understand this task one? Is it clear? Okay, thank you. So then let's I formulate for you the task 2. Prove that the radial component of the velocity is negligible compared to the angular components of the velocity in system 1. This is a thing that which you use in many times, but you'll better prove it somehow. Also prove, this is the end of the first sentences, then related task, everything is here. Also prove that the pressure in equation 11, following from the angular component of 1 and the first equation in 7 also can be neglected. So let's give you some instruction how to better to make this proof. Just again write down for proofs. Use the incompressibility condition 2. Incompressibility condition is just divergency of V is equal naught. The radial boundary condition from 3. From 3. And the necessary asymptotic consideration presented in this chapter. Okay, this is not so difficult task, I hope so, and you can solve them. But the third task I will give you by myself in detail. Okay, let's remove that. Okay, let's again write down this, the formulation of the task, then I will present you a solution. So this is the third task, so its number is 3.4.3. Let me say you formulation of the task. Express from the first radial equation of system 1 or 7, actually system 1 or system 7, they are almost actually in our case equivalent. Express from the first radial equation of system 1 or 7 and from the second equation 214, this 214 is from the previous chapter. So 2 is the number of the chapter. 2.14. The pressure P pressure P and its gradient in the boundary layers and in the main volume as the functional as a functional of the functions So we ask of the function us for geostrophic flow and this free function. Maybe you remember them. That function were introduced in section 3.3 and 2. Actually from all the previous equation we solve, and some of them are here. Okay, let's now to try to find the solution. Okay, we express, so the situation is, if you follow my step, you see that I express the different component of the velocity, but for the moment I forget about pressure. It's partly because this pressure was somehow from the leading order is removed. Only radial component of the pressure appears, but this radial component is not important for us in estimation of the velocity. But nevertheless, some pressure appears. So we, to find this pressure, we in some sense should go in the next order of this approximation. So we express pressure through the geostrophic differential rotation from 215 and the additional pressure delta Q. Okay, so we suppose that there is some additional pressure delta Q. There is some additional delta Q in the Ekman-Bandelier layer. And this additional pressure should work like that. Because, of course, there is some geostrophic pressure which related to the gradient of the P. And to get the P itself, not the pressure, so we should take the integral from 0 to S, whereas this cylindrical radius of U S ds, of course, and this addition of this, maybe it's better to say shear layer. So it's constitute delta, which is e to the half of the delta, which is e to the half of the Ekman number related. You know that because you're already accustomed with that. And then also there is some Q, which is additional pressure. And here, why we use this delta? Because if we take the radial gradient of this Q, then we have effectively we divide on this delta. So these two delta are cancelled, and so this is contribution in the boundary layer becomes of order 1. This is the trick. And this Q is, of course, like this free function and everything we showed before on this. Oh, it's impossible to see, I don't know. So what happens? It's clear on the screen? I don't know. Oh, it's okay. Yeah. Thank you. Okay, thank you. So based on the previous, okay, I didn't finish it. So this contain dependence of theta over xi. Of course, different in the different boundary layer. And also this P is actually depend only on, in the major part, on S, but in the boundary layer, it's mainly depend on the singular variable and theta. So we should estimate this integral. Based on the previous problem, we write the radial component of equation 1 and the corresponding solution for the change in the pressure gradient and the Ekman layer as. As I already told you, if we take the radial component, effectively we not take the radial component, but we take the stretched component, this one. And it effectively removes this delta. So eventually we have this equation for this addition to the pressure, which is Q. dq by dx minus 2 sine theta u. Actually, this is equal not, but maybe I will write short like that. It will be the same. And the second equation is actually the constitute this integral. And we can write down that the Q from another point of view is sine theta so just follow from this. Maybe better to show such an arrow because it's following. Okay, I can also use the comma. So 2 sine theta u integral u dx. This integral, of course, in xi. So the last integral is expressed in outer index O at the top and inner index I at the bottom layer as. There is actually rather a bit lengthy formula, but I try to fit it. Okay, so we can express, there is different expression for the different position. So we can express like that. Okay, on the top we will have the outer boundary representation. On the bottom we have inner boundary representation. So we take here Q naught from theta minus 2 sine theta egret naught from theta and also we have this integral, and because this integral for the stretched variable, we take the stretched variable at the outer point as a limit. But we can, as far as I already told you, if we go from the outer boundary to the inner boundary, so we are going down in sense of the radial. But it's not exactly the radial, it's actually a radial value divided by this very small theta. So it becomes a very big value, and it could come even up to minus infinity, and it's negative because it's diminish all the stuff exponentially. So here, to make sort of the exact correspondence that all this stuff is vanishing, we should put the minus infinity. And here we have the real part. Of this, another part of the resultant exponent square root cosine theta e plus 1 theta okay, here the real part of this, and this integral over dx. And for the, we have the similar, quite similar stuff for the inner boundary. Some arbitrary function QE minus, again, 2 sine theta y theta. And here we have another integral, because I already told you, if we go in outside from the inner layer, we are going in the direction of the rising radial derivative, radial stuff. And because it is stretched, actually it's extended up to infinity. And eventually all this stuff are vanishing. Again, real part. We are taking the real part. But here there is some small difference. Exponent square root of cosine theta. And here we have I plus 1. Oh, sorry, we have plus 1 on the top, but on the bottom it's minus. Just to satisfy all the conditions. And this is another xi, and we take dxi. Okay, so we can precisely calculate these two integrals, and the result is, maybe I will not rewrite this all the stuff. I just simply show. Show the results. I will take the result that all this integral, you just can write separately. Let's just to represent this integral. Of course, the initial values are the same. So we see that this integral is equal, finally. Of course, the multiplier is the same, minus 2 sine theta and free function y0 from R from theta again, yeah. And we have not integral, but the real part of this resulting expression. Here there is the cosine theta. E plus 1 theta O. And here there is the denominator, which quite clearly also has the same structure, but slightly different. Here we have square root of cosine theta again. Here I plus 1. The only difference is that here we have under the exponent and here under such a situation when we integrate that. So we are finding integral and show it this way. Oh, maybe I was wrong to write down this. I reproduced it all with the produce it all this stuff. But let's reduce our problem for the lower part and reproduce only the integral, which we constitute the final solution. And this only integral is the real part again. Of the E square root of cosine theta and in this case I minus 1. I is this imaginary unit, you know. And of course the below things is also quite similar, quite symmetrical. Cosine theta I minus 1. So this constitutes the final solution. Okay, it's a bit tricky formula, but nevertheless it's in some sense exact formula. So here expression 315 is used, and R correspond R, this re value correspond to the taking the real part of a complex number. And finally, if we combine all this stuff together, the required expressions for the pressure gradient. Let's write it down and it will be the final. If you are interested in some intermediate step, of course you can do that by yourself, but here it seems I have no time for that. But let's just write down the final result. Okay, we will keep just this result for this integral. One and second one, just for the reference. And the final result is, first of all, to represent gradient P. So it will be 2 U capital from S, grad S. So it's obviously because it depends only on cylindrical radius, so it depends on the gradient S. Then we have next contribution. which come from the outer layer, and it's no wonder that this pressure has only geostrophic component, which is of order 1, and so it's keeping to be important. And also the next component is purely radial component, and it's constitute, of course, 2 component. It's look like that. And it's constitute the free function y, but which we defined it with you before. Just minus if we open all this real value and to get the final result. So we have this uy function and exponent cosine theta cy, and it's multiplied by cosine from the square root of the cosine theta, so rather tricky estimation ci, and then minus, let's go here. So this is contribution from the geostrophic flow, this contribution from the inner boundary, and the next contribution is obviously from the outer boundary, YO. Of course, these 2 functions are dependent on theta. Again, we have epsilon and another sign, as I already told to you. And then again, cosine square root from the cosine theta C naught, CO, sorry. So we close square brackets, and as already told to you, this sort of singularity contribution in outer layer and inner layer, inner layer and outer layer in this order. So here there is only radial component, grad R. Okay, so it's finished this problem. Solution. And this actually solution we later use for estimation of the shear layer and everything to completely complete the task. Okay, it seems that it's time for the question. Please raise your question. Yeah. This geophysical, you mean geophysical flow? Yeah, this is coming from the very first thing which we started, geostrophic, no precisely geostrophic flow, not geophysics, just geostrophic flow. Yeah, so this geostrophic flow is coming out from the general solution. But to find it precisely, we should accommodate not only the Ekman boundary layer. At the moment, we just via some not yet just physical, just perfect flow. But when we proceed to the shear layer and other layer, which finally formulate the flow, which finally formulate the flow. So then we define precisely what will be the just trophic flow. And it will be, as I already told you, this just trophic flow will be, when we apply all these conditions, it will be the first step, sort of the first order approximation. So at this first order approximation, we precisely determine just from the boundary condition and from the shear layer condition. Then we determine that this just trophic flow is rather simple. As I already told you, there is a rigid body rotation outside the tangent cylinder, and also it will be some change inside the tangent cylinder, but quite smooth change. So there is only jump on the tangent cylinder itself. On tangent cylinder there is a shear layer which is responsible for this final picture. Yeah, so eventually we define it precisely. Of course, it will work in the case, in any case, because we are considering only specific case, and there is a differential rotation, nothing. There is no bind support, there is nothing. If we are the bind support, but in this case, when there is only differential rotation, at the moment we keep the general. But later, in the next chapter, we will go to the precise form, which is enemy for our task. Is there any more question? S is here. S is cylindrical. Del S. It's gradient. Okay, we speak almost about 1 hour. Very much for your Professor Rami, since that it's over, you can stop. Or maybe you have to look at it.
Your task. It was assigned. So quick introduction. What you have to do. And we will share also. Don't worry. We want to show it first. After that, you just open your break and then pick me up. 7:30 is the cultural program. Today I posted na. Games.
So task 1 here, the formulas 0 and 1 are mentioned. Yeah. So let's do it like this. Here is task 1. Yeah. We can make a photo or something, and let's check what we've got as system. Thank you. System 0 and 1 here in our list, and compare it with your notes also. So 0, it's just a definition of viscosity, this one. Yeah. And 1, it's shear stresses in the forms of vector. So that's about first task. So we can even, so what we can do, we can check, you've got your shared lectures, yeah? First 10 lectures, yeah? So also let's check the numeration. No, it's here. Lecture 2, it should be. Yeah, so this formula and so first 2 slides of lecture 2 you need for this task. And for the second task of chapter 1, yeah, repeat. For the second task, here we need formulas 13, 12, 14, and 15. So let's check what we've got in this case. Yeah, it's just definition of total velocity in the rotating system. Navier-Stokes equation, and modified pressure. So that's all. So that's all with chapter 1, and going to chapter 2. This geostrophic flow and all this stuff. We've got these 2 tasks also. Here just the text of this task. First one, perform Taylor transformation to obtain the dimensionless system 5 from the dimensional equation 0 and 1, provided that variables are transformed in accordance with 3. So let's check how it looks like. So we need 0, 1, 5, and 3, all in term. 0 and 1, it's our initial set of equations and boundary conditions. System 5, here it's just dimensionless system. So Rossby number and Ekman number appears. Why they appear here? Because we used this set of scaling. And also, let's take a look at what this lecture. This lecture, I guess, supposed to be this one. No, sorry. Guess this one. Yeah, it's lecture 8. So these formulas 0 and 0, 1 in lecture 8, and in the next lecture, lecture 9, we've got non-dimensional system 5. I hope. So yeah. So this is the scaling. And this is our non-dimensional system 5. So that was task 2. And last lectures, they are not shared with you yet, but I guess in an hour they will be shared. So let's also check the tasks for chapter 3. Chapter 3, and Rossby number and small Ekman numbers and layers. So the first task is quite simple. Yeah, we just want to rewrite vector equation 0 in the form of system of scalar equations in spherical coordinates. So let's take a look at these equations. So this is the initial equation, equation 0, vector equation. And then we just accurately rewriting it in the form of free scalar equations as a spherical system because of this vector Laplacian here. We've got not very nice system nevertheless. So that was the first task. And the second one, where is the second one? Yeah, second one, prove that the radial component of velocity is negligible compared to the angular components of velocity in system 1. So it's just scaling. You're working with very thin layers. You know that radial derivatives were huge, and you need to balance the terms in the equation to be of the same order. That's how you may receive and prove these results, that some components of velocity are huge, some are not. So what equations are needed here from your last lecture? 11, 7, and initial one, 11 and 7. 11th equation, yeah, it's this dispersion relation lambda, and 7, where is our 7? 7, yeah, again, it's initial equation, but for the stretched variables inside the thin layers. Okay, so these lectures, these last 3 lectures, and it's chapter 3. Yeah, will be shared. So these 2 tasks, yeah, you can also do. And the last one, this task, yeah, it's still here on the board, expressed from the first radial equation, from the second equation, the pressure and gradient as and this gradient in the boundary layers. So yeah, it was done recently, so you know the solution. You don't have to do this one. Okay, so that's also all in all. First 2 tasks were kind of solved. So you've got 1, 2, 3, 4 tasks, yeah, to be completed. Yeah, if you want to feel these equations, you need to do it. Okay. Oh yeah, that's all. You can stop. And of course, yeah, if you've got any questions, you know, we've got group chat. Yeah, so you may right there you may ask now. You all possible means you can use.
Start the next one. It's next week. So tomorrow we're going to have some tomorrow is, yeah. Tomorrow it's the morning. In the morning we put some, yeah.